So imagine this, an electric car crashes. Firefighters arrive and they control the fire. The vehicle is moved away and everyone relaxes. The danger actually seems over, then hours later, smoke appears again. The battery starts heating and the fire returns. This is not a movie scene. The US National Transportation Safety Board has documented this risk. This is called reignition, and the main process behind it is a thermal runaway. One cell heats up, that heat triggers more reactions, and those reactions produce even more heat, and the process can spread. Now, think about this. So, what if we remove the flammable liquid from the battery? And what if we replace it with a solid material? Would EV fires disappear or would the car travel further? So could it charge in just a few minutes? So I am Dr. Arun, and today we will test these claims not through the advertising but through the evidence. And the answer is not as simple as it looks. So let us open the battery. A normal lithium ion battery has four main parts: a positive electrode, a negative electrode, separator, and liquid electrolyte. And liquid carries lithium ions. And think of it as a route that electrodes are two cities and lithium ions are the travelers. And the electrolyte connects them. So, this is only an analogy, but it helps us to see the basic idea. And today, this route is usually a liquid and it moves easily through the porous electrodes and all. And this is useful. But many liquid electrolytes are also volatile and flammable. The solid state battery changes this part completely. The liquid is partly or completely replaced by solid materials, but there is a catch. Not every solid state battery is fully solid. Some are semi solid, some are almost solid, and some are all solid state. So, label alone cannot tell us every little aspect. We need to know what is actually inside. Now comes to the biggest promise: safety. Remove the flammable liquid, remove leakage, reduce vapor, reduce one major source of fire. This is actually real. Studies involving in Sandhya's national laboratories compared different battery designs. In some external fire conditions, solid state batteries release less heat, and that is encouraging. But now change the failure. Imagine an internal short circuit. The battery still store a large amount of energy. The cathode can still overheat. The lithium metal can still react violently. And some cathodes can release oxygen. And the solid electrolyte can still crack. Once it cracks, lithium may find a path through it. So, yes, solid state batteries may reduce fire risk, but they do not remove every danger. So, the correct conclusion is simple: safer does not mean a fireproof. The electrolyte matters, but the full cell matters more, and the complete battery pack matters most. Now, let us talk about the range. A solid electrolyte does not create the extra energy, and the real opportunity comes from the anode. And most current batteries uses graphite. Actually, graphite is reliable, but the lithium metal can store much more charge for the same mass. And that sounds ideal. A lighter anode, more energy, possibly more driving range. Some designs even remove the anode material at the start, and these are called anode-free cells. During charging, lithium deposits onto the current collector. Again, it sounds perfect, but laboratory cells can be misleading. Many use thick lithium foils, very thick. Some studies use more than 200 micrometer of lithium, and practical cells may need something closer to 20 micrometer. Why does this matter? The extra lithium helps the experiment. It hides some losses. It improves cycling, but it also adds some weight. It takes space and it lowers the real energy advantage. So, a higher number in a small lab cell does not automatically mean longer range in a real car. A cell is not a pack, and a pack is not just active, as an active material. Now, the most exciting claim: the 3-minute charging. In 2016, Kato and colleagues reported a sulfide electrolyte with a very high ionic conductivity. So, ionic conductivity means one thing, how easily lithium ion can move through the material. And their laboratory cell operated at an 18C rate, and that is roughly a 3-minute charge or discharge rate. Impressive. But look closely, the especially the low resistance was demonstrated at 100 degrees Celsius. That is not a normal EV charging condition. And the fast charging is not only about the ion speed. The ion must cross the interfaces. They must move through the cathode. Heat must escape, and lithium must deposit evenly. If it deposits unevenly, sharp structure can grow. They are called dendrites. Leo and colleagues observed such a structure in the sulfide cells. They moved through the electrolyte and eventually caused short circuits. So the 3 minutes result is important and it proves scientific possibility. But it does not prove a 3-minute EV charge at room temperature. Not yet. So this is where many promising technologies struggle, the laboratory and the real world. So in laboratory, the cell is small and the material is carefully prepared. Pressure can be very high. That pressure keeps solid particles touching each other. But a car battery faces different conditions. Road vibrations, temperature changes, repeated charging, repeated expansion, repeated contraction, and thousands of cycles. A 2024 study gave the same material to 21 laboratories, and that material were the same. The result were not. Why? Because different pressure, different processing, different electrode composition. Some cells used separator around 500 micrometer thick, and the applied pressure ranged from about 5 to 400 megapascal. That is a huge spread. It tells us something important. What? The field does not yet have one mature testing method. The record in one laboratory is useful, but the industry needs repeatability. Every cell must behave almost the same again and again and again. That is called reproducibility. Without it, the mass production is impossible. Now look at the global market. It is moving fast. According to IEA, the global EV battery deployment reached about 1.2 terawatt hours in 2025, and that was nearly 30% higher than in 2024. At the same time, LFP battery becomes even more important. The LFP means lithium iron phosphate, and it accounted for more than 55% of global EV battery deployment. What is that important? Because LFP is already cheaper, already commercial, already improving, and relatively thermally stable. So, solid state battery are not competing with an older technology. They are competing with a technology that improves every year. Semi-solid battery have entered the limited commercial use, but almost solid and all solid state batteries remain at a prototype or pilot scale. But companies have announced future launches dates, such as Toyota, BYD, Samsung, and others too. These plans matter actually, but they are still projections. Until the cells are produced at a scale, we do not know the final cost. We do not know the real warranty life. And also, we do not know the fully safety record. India's situation is different. Electric car actually matters, but two-wheelers matter even more. So, do three-wheelers? According to IEA, India sold around 1,65,000 electric car in 2025. Electric two-wheeler sales were around 1.29 million, and that changes the question. India does not only need the maximum range, India needs affordable batteries, heat tolerant batteries, vibration resistant batteries, and easy to survive batteries, and safe batteries. So the government has approved 18,100 crore for advanced chemistry cell production linked incentive scheme, and the target is 50 gigawatt hour of manufacturing capacity. And by February 2026, 40 gigawatt hour had been awarded. But this program is technology agnostic. It does not prove that India already has commercial all solid state battery production. In the near term, India may gain more from better manufacturing, better battery management systems, better thermal protection, certified chargers, stricter testing, solid state reaction research is important, but it cannot become an excuse to ignore present day safety. So, what is still unsolved? The first is interfaces. Actually, liquid fills gap, solid do not. So, during cycling, solid surface can lose contact, resistance can be increases, cracks can be appears, performance falls, and second is moisture. Some sulfide electrolyte conduct ions very well, but moisture can make them to release toxic hydrogen sulfide gas. That means dry rooms, gas monitoring, careful handling, and the third is self discharge. Even a tiny electronic leakage current can slowly reduce storage charge. Fourth is recycling. Oxides are different from sulfide are different from halides, polymer are different again. So one recycling method may not work for all of them. Fifth is full pack testing. The battery must survive fire, crush, vibration, fast charging, aging, heat, humidity, and real road conditions. A non flammable material is good to start, but it is not a safety certificate. So, will solid state batteries solve EV fires? So, not completely. They can remove one major flammable component, that is liquid electrolyte, and they may also reduce heat release in some failure conditions. But the risk does not disappear. Internal short circuits can still happen, and the lithium metal can still react strongly, and the cathode can still overheat. What about the driving range? So, the potential is strong. Solid state designs may store more energy inside a smaller or lighter cell, but the real range depends on a complete battery pack, not just the chemistry. Actually, pressure hardware adds weight, cooling system add weight, caching and safety system add weights too. And what about the faster charging? So, laboratory results are impressive, but the proof at EV scale is still missing. We need fast charging at room temperature. We need long cycle life. We need realistic electrode loading. And we need low operating pressure. And also, we need lithium to deposit safely and uniformly. All of these must work together. This is the real challenge. So, solid state battery are not a magic solution. They are a powerful engineering platform. They may first appear in premium vehicles or specialized applications, then with a better manufacturing and larger production, their cost may gradually fall. But the safest future EV will not depend on one material alone. It will require better chemistry, better manufacturing, smarter battery management, effective thermal design, and rigorous testing. That answer may sound less dramatic, but based on the evidence available today, it is the most honest answer.